hierarchical clustering. Yeah, hopefully you still remember. We have we have k-means, we have hierarchical clustering, and then today we will learn about density-based clustering. I will review this and then we can do with the programming. Okay. Sorry, density-based clustering. The density-based clustering focus on the density of the data. Okay. For the basic one, we have a DBS scan. So DBS scan is like the k-means is the most basic algorithm for clustering, but this one focus on partition. But the DBS scan focus on density base. So the data or the algorithm focus on the density of the data. Okay. In DBS scan, we have at the first time we have to determine the density. Density here defined as number of points within a specific radius. Usually they use EPS. Okay, so for example, this is the core, for example. So this is the radius, size is EPS. Density is number of data inside this radius. This is density. Okay. A point is a core point if it has at least a specific number of points within this one. So for example, this is the point. This is another point. Point A, point B. Okay. And before this, we have decided or we determined the EPS. Okay. Let's say this is the radius for point A, EPS. So we have this, and also B, for example, this is the radius. Okay. Then we calculate how many points, other points, I mean, inside the radius. For example, for A, we have 1, 2, 3, 4, 5. So there is another 5 points. And this one, 1, 2, 3, 4, 5, 6, 7, 8. This is 8. Okay. So between A and B, which one is the core point? So the core point determined by minimum points, minimum PTS. So for example, we also manually determine how many minimum points inside or around the core point. For example, we decided, a point will be a core point if it has minimum 6 points around this point. So between A and B, A has 5 points around A. B has 8 points around B. So this point A, because this is less than minimum points, so this is A is not core point. But B, it has 8 points around, so this is greater than minimum point. So this one, B, is the core point. Okay. Sorry. Don't forget to count the point itself. I increase it to 7. Okay. So this is 6, still less than minimum point. This is 9. Okay. Including the point itself, sorry. Okay, this is the core point, this is density, and border point. Border point, it is not core point, but it is in the neighborhood of core point. So this one. This. B is core point. So the border point is the neighbor of the core point. So this one is the neighbor of, this is the border point. Then we have noise point. Noise point is a point outside the border, not in the core point or border point. Yeah, so outside. So okay, we here I have a picture. Okay, this one, for example, if the minimum point is 7, so A, why is 1, 2, 3, 4, 5, 6, 7. Okay, we have 7. Okay, so A is the core point. So this is the area of core point. Okay, for example, then we have this one as the border point. Still in the radius of border point, the same radius. Yeah, we have the same EPS. We have another radius, another area from the border point. Let's say this is the farthest border point. Okay, so this area is area from the border point. So what is the noise point? The noise point is point located outside core and border. Okay, like this. So other points outside these two areas, they are the noise point. Okay, noise point. Okay. Yeah, for example, this is the clustering result. So this is the original points. And then we have the results on the right side. Okay, so the green one is the core point. From this picture, we can see that, of course, this is the core point because the density is very dense. So many points around here. You can see this. And when we go outside, the blue one is the border point, which is the point still quite near with the green one. And we have the red one quite far away from the core point. Okay. Okay, so for the algorithms, uh, first we have to, of course, we have to determine the EPS. We have to determine the minimum PTS, minimum points. Okay, and then we can label all point. For the first step, we label all point as the core, border, and noise point. Then we can eliminate the noise point. So we focus on core and border. Okay, like this, how to focus on core and border. Put an edge between all core points within the EPS of each other. Okay, so we focus on the core point. We focus on core points within the distance. Okay, and then make each group of connected core point into a spread cluster, and then assign each border point to one of the cluster of its associated core points. So actually, simply say we focus on which one is the core point. For example, okay, this is the core point. I don't write all the, okay, maybe like this. This is the core point, for example. This is also the core point. So we will determine which one is the border one. So after we identify which one is the core point, we identify the border point. Then we eliminate all the noise one. Okay. Positive or advantage of the base scan, it can handle different shape or different size. If you try this data using k-means, the result will not as good as this. Maybe they will put like, this is in one cluster, this is in one cluster, for example. Yeah, but first for clustering, we really have to use data visualization to see our data pattern, because we can determine which algorithm we can use based on the shape. So shape is one of the criteria that can help us to determine which clustering algorithm we can use. Okay. DBS scan does not work well, for example, if they have the density is very, for example, we have the data. This is the original point. Okay. For this cluster, what we want is actually this is the one cluster. Density, you can see this density is not very high. This is also okay, medium. Let's say this is low, medium. This is maybe uh, almost high, and this part is very high. Okay, so we use DBS scan. For example, this is two results with different parameter settings. Okay, so here you can see this is the result with 4 minimum points and the EPS is 9.92. So this is the result. And if we have this is the second result, the EPS is 9.75. So the blue one will be categorized as the noise point. So the cluster is only 1, 2, 3, and 1 and 3 in the same cluster, although it's different because it's only because this cluster 1 and 3 has the same density. Okay. Yeah, so other points all categorized as noise point because the density is very low. Okay. Okay, this is just the how to determine the EPS and minimum points. Okay, the idea is for points in a cluster, they actually have a k nearest neighbor that are close distance. Okay, noise point have this k nearest neighbor at farther distance. So we can use the plot to sort the distance of every point. For example, this one, we have the on the x1, this is the sorted point sorted according to distance of the four nearest. If this one, if we use the k is 4, yeah, so we can use this one just for example. Okay, okay. Before we go to the code, I will also discuss for the hard and fuzzy clustering. Okay, so this is for DBS scan. Yeah, we can use the program for this because it's quite the computational is quite complex. Not complex, it's the simple computation, but so many things have to calculate. So not like the K-means. In the K-means we can learn manually because it's the computational is not too many, but for DBS scan is there are so many calculation, so it's better to use programming already. Okay, I will continue directly to the fuzzy and hard clustering because you can, I think for you, you also can explore fuzzy clustering instead of only hard clustering. So far, we only learn about hard clustering. Hard clustering means that cluster, one data point only belongs to one cluster. Okay, but fuzzy clustering, uh, what one data point, it has a membership value to all clusters. Yeah, for example, like this data. So it can be belong to the blue class or the red class. Yeah, but we have the value letter about how certain this data point belongs to the red class and how certain if the data belongs to the blue class. Okay. Fuzzy clustering techniques are based on the fuzzy set theory. Okay, this one. Yeah, so this is the basic theory for the fuzzy clustering. Basically, it will provide a natural techniques for producing a clustering in which the membership weights have a natural interpretation. So here, the membership wage, we will have the weights of the membership, which will give us the natural interpretation. So which one is belong to which one. Of course, based on the fuzzy test set theory, the degree, membership degree is between 0 and 1. Okay. For example, we have two clusters. Sorry. Cloudy days. In linguistic, it is defined as a day belongs to the cloudy day if 75% sky is covered by cloud, and otherwise it is non-cloudy day. Okay. So what happened if we have a data point? So for example, today the sky is 50% covered by cloud. Okay. So we can say that, oh, today is cloudy. Okay, today is cloudy, but we have 50% degree of truth. So for example, this is cloudy. This is non-cloudy class. This is the non-cloudy, for example, and the data is here, 50%. Okay, of course, 100% is, of course, this is the cloudy, and 0% is non-cloudy. Yeah, but not all the data, not always every day, cloud 100% cloud or 0% cloud. Yeah, sometimes we have 50% cloud. So that's why we can use a fuzzy to determine, or today it can be belong to cloudy day, it can be belong non-cloudy day, but we have 50% or 0.5 degree of the truth. Okay. This is the fuzzy cluster. We have, for example, the data set X. We have M data points inside the set. Okay. And we have n dimensions. So the data is x11, x12, yes, like this lah. This is the attribute. The attribute or the dimension is from 1 to n, and the data points is from 1 to m. Yeah, this is the data. Okay. And we also have a k number of clusters. K number of cluster. Okay, we have C1, C2, and the CK. Okay, is a subset of all possible fuzzy subset. So later on, each data point will belongs to all cluster. But of course, for each cluster, they will have the membership degree. So each data point xi in cluster J will have membership degree wij. Okay. Mathematically, according to fuzzy theory, the total membership degree for each data point should be equal to 1. So for example, we have 3 cluster, cluster 1, cluster 2, cluster 3, for example. Then we have this data point. Oh, no, not here, maybe here, in the middle, xi. Xi can belongs to cluster 1, can belongs to cluster 2, belongs to cluster 3. But it has the membership value, sorry. So we have wij. W, let's say this is x1. W11 means that degree of membership for xi in cluster 1. W12. So this is the membership degree of x1 in cluster 2. W13, this is the membership degree in class 3. Okay, let's say, oh, maybe this is which is the nearest one? Okay, maybe C1 is the nearest one. So maybe this is the 0.4 because it's quite near to cluster 1. To cluster 3, also quite near, but not as close as class 1. So maybe this one 0.3, maybe 35, let's say 35, okay. And it goes to, oh, sorry, I mean this one. This is cluster 3, and to cluster 2, quite far, so it will be 0.15, 0.15. Okay. The total membership degree should be equal to 1. So for each data, for data x1, the total membership degree to all classes, it should be equal to 1. So this is the meaning of this equation. And also, what is this? Oh, okay, this is the membership degree for okay, this is the membership degree for the value. So it should equal less than m for each cluster. M is the dimension. Oh, no, sorry. M is the number of data. So for each cluster, we calculate all the degree, membership degree of the data should be less than the data itself. Okay, therefore, this is the most important one. Okay, so we can start from fuzzy C-means, because fuzzy C-means, I think you know already about K-means, the most simple one. So fuzzy C-means is the fuzzy version of K-means. Okay. In K-means, we will consider the SSE. Similar, in fuzzy C-means, the objective also want to minimize the SSE. But here, we now, because it is fuzzy, so we have weights of the membership value, right? Wij. So here we have the membership. In K-means, we don't have W, but because of fuzzy, we have membership degree, so we have W here. Okay. P is the exponent that determines the influence of the weights. Okay. So in K-means, we only consider the distance between the data point. Let's say this is xi, x1, xi, sorry. And this is the centroid. Let's say this is the center of class J. We only consider in K-means, we only consider distance between these 2 points. But in fuzzy, we also consider the membership value. So we also consider Wij. And P will determine how big is influence of the weight. If we choose the P is 0, means we don't care at all about the weights, then it will becomes the K-means. Yeah, because if Wij P is 0, then there is no weights. So it becomes K-means. Yeah. So if we increase the P here, then it will become fuzzy. Means that we consider more about the membership value. Okay. And we have fuzzy for SSE. Of course, we also have fuzzy for centroid. Okay. So this is the centroid, fuzzy pseudo partition. This is the equation. So in K-means, centroid is the sigma xij, which is belong to Cj divided by number of Cj, the average. Okay. But for fuzzy, we will consider the membership value. So this is the equation. Okay. And then updating the weights. Okay. We have to update the weights. So this is the equation to update the weights. So every time after we update the centroid, we also have to update the weights. here we update the membership degree of each data point for each cluster. Okay. Okay. This is the differences, the algorithm differences between k-means and c-means, fuzzy c-means. Okay. In k-means, oh, sorry, both of them, we also have to determine number of clusters. Same, yeah. So for c-means, k-means, number of cluster, we have to know at the beginning how many number of cluster. Then, first step, in k-means, we generate initial random centroid. But for fuzzy c-means, we generate the weights randomly. So different. Okay. And step 2 in k-means, we assign the data into the list cluster. Here, as in c-means, we update the centroid. So we generate the weights first, and then we update the centroid. After that, we update the weights. So this is the differences in algorithm between k-means and fuzzy c-means. Okay. Stopping criteria. In stopping criteria, in k-means, we can calculate differences between all and new centroids. Okay. In fuzzy c-means, for example, we can use if the SSE is lower than a tolerance limit, then we can stop. Or another alternative for stopping criteria, if the absolute change of the weight is below a given threshold. So we calculate the differences between the weights before and after this one, before and after updating. We calculate the differences, and if it is below a given threshold, then we can stop. It means that the data is not changed anymore. It's not moved to different cluster anymore. It's already converged. Okay. This is fuzzy k-means. Sorry, fuzzy c-means. Fuzzy c-means applied to the sample data. So for each data point, we'll have a membership value. Okay, this is the color here. I just can show you the maximum membership value. Yeah. Okay. Okay, so after we get the cluster result, we have to evaluate our cluster. For example, how good is our clustering? So there are many cluster validity measurements. Okay. Measure of cluster validity. Okay. Numerical measures, they are applied to judge various aspects of cluster validity that are classified into the following two steps. We have supervised, we also have unsupervised. Okay. For supervised data, for example, what is supervised data for clustering? Usually for this one, the objective is we want to evaluate or validate our clustering algorithm. So here we apply our algorithm into a data which actually has already the class. For example, we have one algorithm for clustering. For example, let's say algorithm A. And we want to evaluate, is it a good algorithm for clustering or not? So how to answer that question? We will apply, for example, this algorithm into a supervised data. For example, iris dataset. Iris dataset is supervised because we know already the class of the data. Yeah. But why we still want to apply clustering to iris? Because basically we want to evaluate how good is our A algorithm for clustering. Yeah, so we test our algorithm. We know the answer already, but we want to test how good is our algorithm. Okay. To measure the extent of which cluster label match externally. So at the class label, we can use this kind of value entropy or other. For example, we can use accuracy. We can use what yeah, error accuracy, error value. Because why we can calculate the accuracy? Because we can compare our clustering result with the actual class. So we can calculate the accuracy. Okay. But how if our data is unsupervised? For example, okay, all real data for clustering is unsupervised because our objective is we want to find the class. Of course, for now, we don't know the class. Yeah, so the data is unsupervised. So how to make sure our A algorithm is good? We cannot compare the class because it is unsupervised. So here we can use some cluster validity, for example, sum of square error or other clustering, some cluster validity. Okay, so we focus on unsupervised data for the real data, for example. Okay, we back to the main idea of clustering. Okay, clustering, a good clustering, it should be able to assign a similar data points into the same cluster, and the similar instance should be well separated. Okay, this is the two key points here. Similar one in the same cluster, different one, different cluster. Okay. So in general, these two idea, they interpret these two ideas into two criteria. They call it compactness and separateness. Compactness is a representation of similar data into one cluster. Separation is the representation of different data put in different cluster. Okay. Nah, this one. Compactness measures the similarity within a cluster. So in one cluster, how similar is our instance? Of course, higher compactness is the better one, or the less variance, yeah, between data inside a one cluster. Separatedness focus on the similarity between two clusters. Yeah, so like this, how different it is. This is the separatedness. Okay. Then, based on these two ideas, there are so many cluster validity formula proposed by so many researchers. Yeah. For example, this is the cluster compactness. Okay, cluster compactness. We have, for example, average distance to centroid. Okay, so here we have this is the centroid and other data point inside one cluster. Then we calculate all the distance to centroid and check the average. Okay. Diameter is the maximum distance. So diameter, this is here. Diameter is, for example, we have cluster here. In one cluster, I mean. Diameter is the farthest distance. So to calculate diameter, we have to calculate distance between pairwise distance. We can find the pairwise distance. So we calculate, for example, this data point to here, here to here, this one to outside this one. Yeah, pairwise that distance. And diameter is the biggest one. It means that it will find out the big range, for example, from here to here. That's the diameter. And then we have sum of distance. Okay, sum of distance, but this is within a cluster. So here we calculate distance again, this is the pairwise distance. Yeah, this is the pairwise distance between each two data point in the same cluster. But here we, like this, we calculate the pairwise distance, but we summarize all of them. Yeah, this one is the sum. This one is the maximum of pairwise. Okay. So diameter and sum of distance using pairwise distance, star and split and cut also using the same star using the pairwise distance also, but star for diameter it use maximum, star using minimum. Okay. Here it use minimum distance between two data points in one cluster. Split. Okay, so split. Split is to calculate distance. For example, we have this cluster C cluster 1, for example. We have another cluster C2. Okay, here we calculate a distance between all data in cluster 1 to all data in cluster 2. So, for example, this one to here, to this one, to this one. And then we also calculate second data to here, to here, to here. And all of them, we calculate the distance. Then we choose the minimum one. We find out which one is the minimum one. That is the split one. Okay. For cut, I think there's some, I put the wrong equation, sorry. Later I will show you. This is the wrong equation, sorry. Okay, I will skip for now. Yeah, but basically for cluster compactness, focus on inside. Okay, and then this is the separation index. So here focus on in one cluster. This one focus on different clusters. For example, the easiest one, of course, this is the distance between centroid. So cluster 1, we have centroid C1, cluster 2, C2, calculate the distance. This is this one. Single link. Single link is okay. They will calculate between each cluster. We have 1, 2, 3, for example, and then they will calculate pairwise distance between data between each cluster, and they will calculate the minimum one. Okay, for complete links, it is the maximum, same like single, but it is maximum. And for group average, they will calculate all distance between each data point here and do the average. Okay, but using NP is number of data in cluster P, and key is number of data in cluster Q. Okay, so all the point, calculate the distance, and then divide it. Okay, so if these two compactness, calculate compactness by only compactness, this is only calculate separateness. Later, there are some others cluster validity which calculate both of them in the same calculation, in the same formula. So in one formula, it's already considered the compactness and separateness. Yeah, so here, another cluster validity, it mix compactness already, compactness plus separateness in one formula. There are many cluster validity index like this. For example, SW, SDBW, And then Shebani index, this is the name of the one who proposed. And Davis Baldwin index, this is also the name of the one who proposed. VI index, and many more. Yeah, you can, if you search like cluster validity index, you will find there are so many. For example, VI index, for example. VI index, this is the formula. Okay. Uh, alpha is parameters, and is the this one. Okay, this is basically the some follow some Gaussian distribution, I think. Intra and inter. What is intra and inter? Intra, this one, intra is the compactness actually. Compactness. Inter is the separateness. So here you can see that they put in the same formula. Okay, why VI put here uh, one parameter or one multiplication factors? Because actually, if we, let's say we have SSE. SSE more focused on compactness. Compactness. Of course, we want SSE as lower as possible. But actually, it is tricky because we can, if we increase number of cluster, the SSE will be lower because of course from big cluster we divide it into smaller cluster. For example, like this. First one we in big divide it into two. Compare if we divide it into, for example, 4. 1, 2, 3, 4. Of course, the green one will have smaller SSE because it is more complex. Smaller cluster will have smaller SSE. But if we divide it into too many clusters, then interpretation will be not not quite good because it's just like the cluster is too small. It's just like the same as we don't make a clustering. Yeah. So here, that's why they in VI they put one multiplication factor here to make sure that the number of cluster is not too many. So the compact we can get a balance between number of cluster and SSE. Of course, here they also consider the separateness. Okay, so this is the basic idea of how usually people propose cluster validation index. Okay, this is confusion matrix, but this only for supervised. So for example, if we want to validate our clustering algorithm, yeah, we can use the accuracy. Okay, now this is the general step for data clustering. Okay, so if we use the data clustering, first we have to do the data preprocessing. Okay, data preprocessing will be at least uh, we do normalization. We also consider to do the outlier detection because most of data clustering algorithm are very sensitive with outlier detection with outlier. Yeah, so if we don't need the outlier, then it is better if we just eliminate the outlier. You also can do the other data preprocessing, including like missing value and many other things. Yeah. And we also have to determine number of cluster. Of course, this is only for some algorithms. For example, like k-means. If we want to use k-means, then we have to determine number of cluster. Okay. For example, the easiest one we can use elbow method. Elbow for k-means, for example. After that, we can do the clustering. Then, after we get the result, don't forget to analyze or do the cluster evaluation using, for example, cluster validity index. We talk about cluster validity index. Yeah, so this is the general step for data clustering. Of course, if this is for implementation. Implementation means that we use the uh, existing algorithm to the real data, for example. But for example, if you want to propose new clustering algorithm or clustering framework, then before this, we also have to apply your new algorithm to supervised data. Supervised data, which actually this is the validation. We have to validate that our new algorithm is good or not. Yeah, so we have to one for validation step is we apply our algorithm into the supervised data because we know the answer already. So we can check if our algorithm is correct or not. Okay, any questions? Any questions? Is it clear? Okay, if clear, then so if you open your Anaconda or your Python, or you can also use MATLAB if you want. But now I think we can use Python first, for k-means and for DBS scan. Okay, this is for our practice, we can use again, we're back again with the iris dataset, easiest one. Okay, so here is the program. Yeah, this is a program for k-means. I think, yeah, I use k-means here. So here, this is the data, input data. Okay, this is for data preprocessing. I use data normalization. This is for pre-processing. Okay, and then after that, from preprocessing, we use data normalization. For iris, there's no outlier, we check already. So I can skip the outlier detection. Data normalization, this is the new data after normalization. I put in xnorm. Okay, so for k-means, this is the number of cluster 3. Okay, why I know 3? Because for iris we know already number of cluster is 3. Okay, and then I put this data to k-means. And here k-means.labels is the predicted label for each data point. And after that, this is the cluster validity. There are some cluster validity provided by Pythons already. For example, SSE. SSE is included in the k-means. So we can just print out k-means.inertia. CH is Kalinski-Harabas. This is one of cluster validity index. And DB score, this is the Davis-Baldwin score. We also have silhouette index. Okay. So means okay. For the rest one, this is only the visualization. Okay, so this is the clustering result. Okay, but how if we don't know the number of cluster? So if we don't know number of cluster, what we should do is for example, for k-means, yeah, we choose the easiest one. For example, we will run the elbow method. Let's say we don't know the number of cluster for the new data. So before we can do the elbow method. So actually, for the elbow method, we will have like this kind of graph. This is number of cluster. This is, for example, the SSE. You actually can use different cluster validity. For the easiest one, for example, using SSE. So here, first we try with that number of cluster is 2. The smallest one is 2. Okay, so here we run this program with the number of cluster 2. And then we get the SSE. Let's say this is the SSE. Okay. Oops. And next we run again with number of cluster 3. Okay. And we get the SSE. Let's see here, for example. Then we calculate again with number of cluster 4. We get here, for example, 5, 6, 7, and as many as you want. Okay, but actually, if the graphic is already like quite, the slope is not high already like this, yeah, you can stop, because if you increase number of cluster, the change will not be significant, and we don't use that part. So we only focus on the elbow area. So here, yeah, is the elbow area. Means that we can choose between, for example, 3 or 4, I think. Okay. So this part, this part for k-means, and we can put here SSE, we can put after we get the k-means. So after k-means, we can get the SSE, and we do this for a number of cluster for n equal to 2. So this part we put in 4 until how many? Let's say 8 or 9. Yeah. Yes. So for this part, k-means and SSE, we can do several times. Of course, we use the looping here for n equal to 2 to, for example, let's say 9, and then we can get this graph. Okay. Then after we can get this graph, we can, okay, number of cluster, I choose, let's say 4. Okay, for example, for our real data set. I choose number of cluster is 4. Why 4? Because 2 to 3, the decreasing of the SSE is still significant. 3 to 4, a little bit decrease. Yeah. 4 to 5 is not significant. So we choose 4. The number of cluster is 4. This is the elbow point. Elbow point. Okay. So, okay, from this, we know how many number of cluster. K equal to 4, for example. Then, after that, we have to run k-means, and the real k-means, with k equal to 4. So after this, then we can get number of cluster. Then we run k-means again with certain only one number of cluster. Okay, so here for the second run for k-means, actually you also can use this, but don't forget k-means. It is very sensitive to the initial centroid. It has the random factor here inside the k-means, so that's why we run again k-means several times here to make sure that our result is already stable. Why we have to run several times? Don't forget we have to evaluate our result. Okay, so why we have to do several times? Because maybe, for example, one running, the cluster result is like this. For example, like this. But other result, the clustering will be 1, 2, 3, 4. Different clustering. Yeah. So we want to find out which one is the best one. That's why we have to do it several times to find or to get the most or the best clustering result. Yeah, so we run k-mean several times. Don't forget we can also print out the others cluster validity, for example CH, DB, or other cluster validity, and see, for example, let's say we want to do 30 times runnings, and we want to see, oh okay, after 30 times it's already stable, so the clustering is most of the result is like this, for example. So okay, this is the final clustering instead of this. Maybe this is the wrong one, this is the correct one. Yeah. Okay, and after that, of course, we have to interpret the result, like what happened with cluster 1, what happened with cluster 2, and other things. Any insight or any information we can get from the clustering result. Okay, can you imagine what should we do if we want to do the clustering? Is it clear? No questions?
None so far, Dr. Farah.
So far is okay. Okay, I would like to ask you one question. If I give you one more assignment for clustering, do you want to do it now, or you in the class? So if you have any question, you can ask me, or you want to do it by yourself. It's up to you.
In the class, I think Arvin Ong will do it.
Dr. Shokik.
Arvin, you want to do?
I,
Because later
I
you
have...
can share to everybody.
Yeah, it's okay.
Grabe.
Okay, share your screen, Arvin.
I didn't... I don't have the code yet. I'm still trying to.
That's why we do it together. That's why we do it together. So I will give this print screen. How to make a print screen? Print screen. Oh no. I think print screen from here and chat. Can I send? Oh, I cannot send print screen here, yeah.
No, you can't.
I can print screen, Dr. Fair.
Okay, you can print screen and you can try. Or any other for other student, if you also want to try, you can try. So we can discuss. This is for k-means, and this is for DBS scan, I think. Yeah, this is for DBS scan. K-means, although it's quite old, until now, actually, there are still many application and still many even advanced clustering algorithm still consider k-means as their basic algorithm. Why? Because k-means it's very simple, very fast, and the result is although some result is sometimes is not good, but in general it can still work well. Okay, Arvin, you want to share your screen?
Okay, doctor.
It's okay. In the class, we all of us we learn,
Okay.
so don't worry.
Uh, okay.
Dave, yeah, that one. You can just type because they give you already. Tap. You can click tap. Okay.
Click what, Dr. Phil?
No, no.
I
Before when you type that Davis, DAV.
Oh, it comes out
Yeah,
already.
yeah.
Oh,
They
okay.
give you information, so you can tap already. Oh, I send you the iris data by. Arvin, I send you the iris from the Zoom chat.
Oh, okay, Dr. Fair. I think it's the same iris code that I
Oh, you have
use.
already? Okay, okay.
Yes. Dr. Farah, why is this an error?
What is the oh line 35? Yeah, predict and then close bracket. Line 35.
This one?
Yeah. Yeah, close bracket.
Oh,
And delete first.
where? This one?
Before that, the underscores, you have more underscores before the
Ah,
close. Okay. And then ch score. Yeah, you in line 33 you use sh. In
oh,
34 you call hh. Yeah, okay.
oh, okay, okay.
Yeah.
And then run?
Yeah. Iris, you cannot find the iris. I haven't put the dataset in the same folder.
Oh, okay. Could I save it?
Yeah. Can you put
What happened?
in Python? This
Okay.
save as type. Save as type we have to change.
Oh, say, save
Save
as.
as, okay. Python file. Yeah.
Oh, okay.
And then the name. Yeah.
Eh?
Min max scalar. Wait. Scalar pre-processing. Why?
Scale.
You don't have
Ah, wrong
scalar.
spelling.
I think wrong.
Wrong spelling.
Scalar. Yeah. Also line
Oh, okay.
32.
Wrong spelling. Eh?
Min max scalar. Which
Scalar
one?
pre-processing has no attribute.
It's min underscores max scalar. Min max scalar. Pre-processing dot. Okay. Line 21.
Mm-hmm.
You can delete that part. Min the big M.
Where? This one?
Yeah, that one. And delete the underscores. Not that one. Min max, the second. You can
Oh,
use
okay,
the
okay.
tips. Yeah. The second one, yeah.
The second one, I
Oh,
changed
no.
this to.
I mean that one is correct. That one is correct.
Oh, okay.
Okay. Yeah. Okay. They give you
Suggestion?
suggestion. Yeah. You can see that one. Yeah.
This one, the second or the
Second
first
one.
one?
Second one.
Okay.
Okay. You have to delete the previous one.
Oh, this one?
Yes.
Okay. Eh?
N cluster, number of N cluster. N clusters. S.
Oh, okay.
Yes.
Ay, grabe.
Inertia. Okay. Line, which one your inertia? Line 31. Yeah.
Oh, it should be capital KM?
Inertia.
Wrong spelling.
Yeah. Okay. Nah, that one. The first suggestion. So when we type the words, they will give us the suggestion.
Yeah.
So we can just use their suggestion.
Ay, grabe. Still has no
Okay.
attribute silhouettes.
You're still drunk, huh, from last night?
Scalar.
Silhouette. The line 37.
Eh? 27.
Yeah. the silhouette.
Spelling na
Try it.
naman to.
Let's see their suggestion.
Eh?
Yeah.
Why? No,
Ah,
Ah.
second the second
second
one.
one. Ay, grabe. I would delete all of this one.
Okay,
This one.
inside the, yeah, you can delete that.
Oh, okay. Like that.
Yeah, okay.
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 Unknown
Oh,
metrics. Ang dami.
okay, can you open your iris data? Let's see your iris CSV.
This one, I think.
No, yeah, that one. Want to see. Okay, so delete the column C because we don't use that for now. Sorry. E. Yeah, the class.
And then just save.
Save, yeah.
Eh?
Yeah.
Oh, it's the same error. Unknown
Mm,
metrics.
unknown matrix. Matrix. Okay. Mm, 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 mm.
Maybe wrong spelling.
Let me find out. Matrix Euclidean. Oh, that one already.
Spelling.
Okay. Okay. So this is the result. So here, SSE is 6.9, for example, CH score and DB score. Okay, but this one, Arvin only run for one number of cluster. So let's say, for example, in this case, let's say, for example, we don't know the number of cluster. So what should you do is for line 22 and 31, we can put in looping. Okay, so can you do looping, Arvin?
No. No.
It's okay. Oh, if other student want to help you, you also very welcome, yeah. Okay, so let's try. Line 31st, you
Okay.
move that right after 24.
24.
Yeah. Okay, and then you can, let's say you can, okay, I give you example for looping in looping in Python.
Oh, okay.
For okay, wait, I think I can show you. For Afin, I will show you for a while my screen, and then you can okay, like this. So here, okay, so here I put the SSE. This is the I will record all SSE for each number of cluster. So line 25. So SSE equal to, and like this, empty array. You can put that before your here. Before, so you can put like this. This one. Okay. And we will use for example, like this. So the k-means and the SSE will be inside the looping. Okay, because we want to have like this kind of graphic. Okay, so you can type for I in range 2 to 21. It means that I will try number of cluster from 2 to 21. Maybe it's too big, I just use until 10, for example. Okay, and this one, don't forget to put some indent using tab. Okay, this one I think I don't use that for this time. This is the SSE. Oh, sorry. SSE. I calculate SSE here. Okay, I don't use this for this time. Okay, and then we will save the SSE value for the number of cluster. Oh, sorry, K means this one number of cluster changed to I, because we are going to run K means with several number of cluster. So I is number from number 2 to number 10. Okay, and then like this. We put this one SS. Okay, I show you both of them. The original line 27, we want to see what is the inertia, but now SSE, yeah. But now we will save the SSE value into the SSE array. So here I change to sse.append. It means that I will extend our SSE array, and then I need to extend because I want to put inertia or SSE. Okay, like this. And then finally I will plot the result. I think for this I will not use that. So the rest of the file, this one, I block and then I click Control 1. So all of this will becomes the comment, because now I will only focus on determine number of cluster.
Dr. Farah,
Yeah,
the
you want to show?
attribute error is object has no attribute on append.
Oh, you can share your screen. Oh, okay. First, let's see. Line 27, you can delete that. And also 28. Okay. Backspace again. And SSE line 27, you can put your cursor at the beginning of before SSE, and then you click tab. Yeah, okay, good. SSE, okay. APPEND, okay, should be. Okay. Okay, means the yeah. Okay, and then from cluster center 31 until the end of the program, you block. Okay, and then you click Control 1. Yeah. Okay, you can try to run. Okay, here now we already get the result. So this is the plot. Is the from this plot we can see which is the elbow point. Which one is the elbow point? Yeah. So for this one, we see in which point the SSE decreasing is not significant anymore. So for example, from 1 to 2, of course, is still significant. From 2 to 3, I think still, yeah, but 3 to 4, it start to decrease. 4 to 5 is not significant anymore. And if you change into more, the number of cluster is more, I think also the line will be almost flat. So we will not choose that. Okay, so here we choose number of cluster around 3. Okay, if you want to find or if you want to do with other data set, because for iris we know already, oh, iris is 3 class, so we tend to say, oh, okay, the 3 is number of cluster. So I think if you have, like, if you want to try with other data set that we don't know exactly how what is the number of cluster, you can choose you can run this program. Yeah,
I just changed this one, right?
yeah, but make sure you have the data. What is your
Yeah.
data?
No, I don't have data right now.
Yeah. Later, all of
Mhm.
you can change the iris, the name in line 14, and don't forget to change the line, say, 17. 4 because we have four attributes for iris. So that one will be number of attributes. Okay.
Dr. Ferrer, if I put, for example, here, would it disrupt the code?
No.
It's okay, right? If
Yeah.
I put note here.
Yeah. Actually, for this data, because the data, the X data is already, is already all is the data set, so you can delete that one. Okay, that one I just
Eh,
want to.
what happened? Why is it
What happened
no
with you?
no further documentation available?
You save in the right folder, is it?
Yes. It's still here.
Oh, the file
Oh,
Python.
grabe.
Yeah, it still can. It should
Oh,
be okay.
wala.
Hmm?
Why is it? Mm,
Click variable explorer or plot. Yeah,
I,
yeah.
okay.
Okay. Yeah. Then after we know already, oh, okay, number of cluster is, let's say, 2, 3, or whatever, and then you can use the previous data set, the previous code to run your result. Okay, and don't forget to uh, analyze the cluster validity. Okay, which one is the good one? We choose the good one, of course. Okay, so hopefully you can understand and you can apply this clustering. And I think if you want to, or other students, you also can explore other clustering algorithm. Yeah, there are so many clustering algorithm. Let me show you. In Python itself, scalar cluster. Okay, thank you, Arvin, uh
Thank you,
for
Dr.
your
Ferra.
okay. Okay. Yeah, you can also try the Basecamp or hierarchical. Optics is also the clustering. The algorithm is quite similar with the Basecamp. Yeah, but they said it is the more general version of DBS scan. Okay, so optics algorithms. This is also density-based algorithms. Okay, you can compare. So if you want to compare, I think DBS scan you can compare with optics, but k-means with DBS scan, if the data from data visualization we can know already, oh, this data, for this data DBS scan is more suitable, so you can choose directly DBS scan or optics. Okay. This for this algorithm, honestly I never use this one. mm, B bridge algorithms. Yeah, I never use this bridge algorithm. I just use k-means, hierarchical, DBS scan, optics sometimes. Yeah, so maybe later you can try. Okay, so I'm sorry because I have to give you another assignment for clustering. Yeah, so I just want you to try how to do clustering. And for the step for clustering, don't forget this one: data preprocessing, normalization, outlier detection. Then we have to determine number of cluster if we use, for example, k-means algorithms. For DBS scan, of course we don't need this. And then we do clustering, and then we do cluster evaluations. If you choose benchmark dataset, sometimes, most of them already give us the correct number of cluster and correct answer, so we can compare our result with the real result. Okay, but if you want to apply your real data, very real data, we don't know the result, so cluster evaluation, cluster validity is very important. Okay. Wrong slide. This should be this one. Okay. This is DBS scan. So this part is still the same. This is the pre-processing, but this one is DBS scan. For DBS scan, we have to determine the EPS, and minimum sample is min PTS, minimum points, minimum instance in for the neighbor to define the core point. Now this is the minimum PTS. The rest is the same. Okay, this is the DBS scan. And okay, so oops. Yeah. I want to share you one my work about clustering. But this is the clustering algorithm has been improved. So this is the title. Maybe I can share you the paper if you want. So here we realize that clustering algorithm has some drawbacks. So what we do in this algorithm is we apply another algorithm. For this paper, I use n colony optimization, which is this one is meta heuristics. Meta heuristic algorithms. Meta heuristic basically is a numerical approach to find the optimal value. Okay, so in this work, basically I try to improve the k-means for clustering. Okay, so to improve the k-means, I apply this algorithm ACO to determine number of cluster and initial centroid. We know that these two issues, these are the drawbacks of k-means algorithm. So improve the drawbacks using this algorithm. Okay. So what we do in the algorithm is before we apply k-means, the ACO here give a find number of cluster. Okay, so let's say the ACO give you number of cluster 3. Okay, 3 is the best number of cluster based on ACO. And then k-means, we know that k-means, original k-means, start from random initial centroid. If the random is good, the result is good. If the random is bad, the result is bad. So to solve these problems, the initial centroid also given by ACO. So after they give, oh, okay, you use 3 number of cluster, and then for each cluster they give us centroid for each cluster, initial centroid, sorry. Then after that, these two information, number of cluster and two initial centroid, give to k-means. So the k-means, where is our k-means? This one. Until this step is done by ACO. But this step is done by k-means, original k-means. Okay. For cluster validity, in that paper, I choose VI index. Yeah, actually we can use other cluster validities. Okay, I just choose one of them, VI index, to calculate or to validate this algorithm is good enough to do the clustering. Okay. Before we apply this new algorithm into the real data, of course, we use this classifiability and algorithm we apply in a benchmark data set, several the benchmark data set, not only one, because we want to test the algorithm. Yeah. Then after that, apply to the real algorithm. The real data. Okay, so what the steps I have to do for the clustering real data? First, this one I use data exploration. This one I use visualization, the simple one, visualization, to see the condition of the data. Okay, so from this picture, okay, I found out that most of the data around this area, but then there are some, I indicate there are some outliers like this. Just indicate from visualization. Okay, and then to support my hypothesis, because this one I just think, oh, I think there are some outlier, but then to support that statement, we use basic statistic approach, simply using box plot. To make sure that, oh yes, there are some outlier, to make sure statistically, because visualization maybe it can be right, it can be wrong. Yeah, so it just initial screening, but then we have to make sure that our visualization is correct. So I use more scientific step. I use statistic approach to make sure that, okay, there are some outliers, using box plot, using this one. Okay, then after I certain that, oh, okay, there are some outliers, so I want to delete that outlier, so I'll eliminate the outlier. This is the new data after outlier elimination. So the data like this. Okay. Actually, if we get this data, you also can try, for example, we can try k-means. Oops. K-means. We also can try DBS scan and other algorithm. We also can try. Because we see here, same area, density is very dense. Yeah. But this one is not really dense. So maybe for this case, DBS scan will not perform well. So I just prefer some k-mean based algorithm. Okay. Then this is the result using k-means. Not really perfect actually, I can say that, because you see, okay, this is the one cluster, another cluster. In some area, cluster is a little bit mixed like this, like this also. Yeah. So, oh, there are 10 number of cluster based on ACO. The ACO algorithm give me answer that for this data, 10 cluster is the best one. Okay, so I choose, we show this result. And after that, of course, we also I also give the cluster validity analysis. Like we show like how good is the cluster using based on VI index, blah blah blah. Some cluster validity analysis. But then because here is the real data, we want more information about this result. We don't stop until this part. Don't stop until just okay, the cluster validity is good enough to get this for this clustering. So after that, again, we have to go deeper about this result. So clustering, basically the clustering, we can use clustering to do the profiling. For example, profiling of each cluster. I think I forgot to mention. So this is the data. Here is we are going to, I use this data, or I use the algorithm to do the market segmentation. Okay. So basically this data, its data point belongs to one one customer. Okay. So for market segmentation for this paper, there are three three attributes: monetary, recency, and frequency. Three attributes. Okay, again. So after we get the clustering result, I try to see a profile of each cluster. That's why here we go deeper into the profile of each cluster. One basic idea is, okay, start from the statistic descriptive of each cluster. Yeah, for example, for cluster 1, there are 28 customer here, and this is the data of in terms of recency, frequency, or monetary okay, for our cluster. And then because this picture is not a little bit difficult to interpret, so I try to make it into one graph. Okay, so here try to use data visualization to help me understanding these tables, because this table is quite difficult to understand. Yeah, so I try to put in using another data visualization. Okay, so this is data visualization of the result. The x-axis is the recency, y-axis is the frequency, color is the monetary, and the size of the dot is the frequency, or how many customer in that cluster. Okay, so here, of course, we need a domain expert about the problems. In this problem, because this problem talk about cluster segmentations, so to understand this result, we need to have some knowledge about cluster segmentation. So here actually, like what time buyers, potential high, low value, core customer, low value customer lapse, nearly lapse. This is all is the this is all the customer segmentation knowledge. Yeah, so to understand here, we have to understand the domain problems. Okay, that's why data mining is not about process the data, but it's about after we get the result, what's information we can get. Yeah. So my suggestion for your research after we can get this custom clustering result, don't forget to give a more valuable information. Okay, like this. This is just one example. Actually, you can maybe other people more expert about marketing. They can talk more about this. Okay. Any questions?
Dr. Farah,
Yes.
for the assignment, what
Yeah.
do we need to do?
Okay. At least for
Publish
you.
one SEI with the clustering
Ay,
method.
grabe.
Wait.
And
So for
publish
your
one more SEI with the supervised method.
okay. So for your assignment for clustering, basically I just want you to try data clustering. Like Arvin, you have done your assignment, half of your assignment. You just complete the
Half?
step.
Half?
Okay. For your assignment, if you want to use your real data, it is okay. But if you want to use some benchmark data or any data in the internet, it is also okay. No problem. Because want you I just want to make sure you know step by step what should be done if we do clustering. I don't want you to only know how to okay from the package Python we can call all this package, but how to elaborate all of this package to get one the correct step for data clustering. Okay.
Dr. Farah, so
Yeah.
for example, what I did was only up until determine number of clusters.
Yeah, what you did is until determine number of cluster. You can continue into you have to do the clustering and cluster validation, and if you like you can interpret the result. Interpret the result.
And write a
The
paper
The
and submit it.
oh,
interpret the result like the first assignment you did.
oh, okay. So the clustering will be the one you discuss after this one, the graph.
Which one?
The do the clustering. It's the
The
one after
oh,
this.
this one data preprocessing. Okay,
Mm,
and then this is the do clustering. So we do clustering. Of course, for this to get this result, I do several times clustering and choose the best one. Choose the best one, choose the most stable result. Because the result may be can be different to each other. XCO is meta heuristic, but it also contains with the random factor. So maybe also can be different.
Dr. Farah, can I
and
ask why you choose ACO?
Uh, I forget. Just I just want to try.
You just want to try. Yeah, I know. I think you just want to try. Okay.
Honestly, I just want to try. Of course, I don't say like this in the paper. Of course
Yeah, I
not.
know. I know. The politicians, I know. So I'm kind of like okay. Now I'm kind of learning the world of the data mining. I mean, you know how we can make paper in the data mining world. If ACO can do it with this one, then we can do PSO with this one. We can do the
Of course. Yeah.
manual with this one. And you test the data of the consumer. What I think you tested this one in the consumer something, right?
Okay, the original data, actually the original data is the data from POS, POS system. So there is one company in Taiwan actually. The company sell women's clothing, and the POS data they record member of the customer. So let's say for customer A, today, for example, today what day is today? April 4, 10, for example. No, April 9 today. This customer A buy maybe buy 2 clothes. The total price maybe for example $100, for example. And then maybe April 10 buy one clothes price is $50. And we have customer B, customer C, customer D, and other things. This is the data from the POS, the cashier machines. Okay. So from this original data, I transform into 3 category. Monetary is how big is my how big is customer A purchase in this store. Frequency is how many times I come back to the store. Of course, a more loyal customer will back to the same store more, right? And recency is when is the last time I came to the store. If I come to the store it's just recent days, for example last week, it means that this customer is still remember about us, for example. But if customer A, for example, we have customer D, last time she bought the clothes total $500, for example, but it was 1 year ago, 2020. So in terms of monetary, it is good because she purchased quite big. But in terms of recency, it's not good because last time he came to the store is 1 year ago. So these informations, basically, if we only learn about data mining, this is the only result I can give you. Like, okay, this is the cluster and this is the profile of the cluster. If I only learn about data mining. So to give more insight, I have to learn about market segmentation. Okay, so from this result, for example, the most reasons is this one. More here is the more reasons. To the right is the long time ago. The last coming is long time ago. Frequency, small one is the customer only come to our store few times. This one is come to our store very often. And the color is the monetary. So the blue one is more expensive. Okay, so for example, cluster 4. From the profile here, we see from the profile in cluster 4. Here, cluster 4 is here. So it's quite recent, come to our store. And the frequency is, or maybe this is a very few, maybe around 1 to 3. One to 3 times come to the store. And the monetary is not quite big. So we can identify cluster 4. Customer in cluster 4 is like a one-time buyers or the new customer because it has come maybe few times and recently come to our store few times, but they only buy a small amount. They only spend small amount of money in the store. Okay. And
Dr. Farah?
yeah.
How do we create the graph, like the slide before this one?
This one,
Yes.
this is using 3D plot.
In Python?
At that time I use MATLAB.
Oh.
But Python also can, of course, Python also can have this. Because this is basic charts actually. So Python also have, MATLAB also have.
So this is the clustering part for the assignment. And then after, yes.
Yeah, after that, if you can continue, if your data is your real data, of course, we can give more analysis because we know the data. But if we use benchmark data set, of course, we cannot give this.
How many
Unless
total
you,
data you have that time?
forget Let's see. I think it is in the paper. I will give the paper to you.
Science
Just
Direct. In
I
Science
give
Direct.
you. No.
In Science Direct, the paper.
Yeah. I can share. I can share now, I think.
Wow, so many papers. Look at that.
No.
Wow. Dr. Farah published 20 something STI. It's so crazy.
Oh, this one.
Artvin Ong, can you be the next Dr. Zulfia?
Yeah, you can.
How I wish.
The next published 20 something STI. Oh,
Send
it's
successfully.
crazy.
Okay. Okay. So for the assignment, don't worry. Just can do until this part is okay. Until this part is okay. But for your own result, my suggestion is until this part. Give more information. Okay. I think Arvin, you show me your data, and also maybe for Myla. For example, your data for your decision tree, you can use the same data. Maybe, yeah, I don't know your real data, and then you can uh, understand the profile of the the one who want to apply to the company. You can have the profile, for example.
Yes,
Alvin also have can profile a student, or no, high school student
Yes,
who
yes.
will join the chemistry or chemical engineering. I forget. Sorry.
Yeah, chemistry related courses.
Yeah, chemistry related courses. You can do the profiling.
Doc Farah, I
Yeah.
just have some clarifications. At
Mm-hmm.
the end of clustering method,
Mm-hmm.
upon, let's say, running it through the Python, will we
Mm-hmm.
be able to also generate the table a while ago? The one besides the graph?
This one.
Oh, yes, that one.
Yeah, you also can get that.
Oh, okay.
Mm-hmm.
We'll try.
Yeah. Uh, the information. Let's see for what kind of output we can get from from the package. For example, using k-means. I think here, this one. So parameter is the input, attribute is the output. So what kind of output we can get? First, we can get the cluster center, and labels. Label is the predicted class of the data. So in the picture, the color of the data. This is the class. And then the inertia is the SSE, and iter is number of iteration used to get the final result. So this is the output.
Okay po.
Okay. I think for some other algorithm also will give us information what kind of input and output we can get. Again, this is DBS scan. Parameter is the input. This one is the output. For the DBS scan, again, we can get the labels. Labels mean the class of the data. Okay. So how many weeks? 1 week? Can you finish your assignment in 1 week?
Yes, they can.
Just make small. Just make it simple because yeah, assignment just for assignment. I hope you can try to do this. Yeah, the real challenge is when you do your research, of course. Okay. Any more questions?
Actually, I have one question with my task validation 1.py, but I don't know why I cannot run this model.
Validation. Which one?
Uh, this file I already sent on chat, doctor.
Do you
Can you
want
see?
to share your screen to show me?
Okay, let me
Okay.
listen.
Okay.
Can you see?
Yeah, I can see.
Yes, it's not syntax thing or like this, but I try to.
Ring I. Oh. Okay. Let's see. Oh. Hmm. Can you delete import in line 45?
What is by
Mm-hmm.
and
pp dot plus dot. I check. Dot plus dot. Dot plus data for this. Tough. This one. You want to. What is your propose to use this one? String IO pp dot
yes,
post data. You want to use the graphics or what?
yes, sir.
Okay. This one you send me. Is it the same one you send me? The tough.
How, yeah. How can I use the order? Can you suggest me?
How can you use what? Sorry.
Yeah.
Oh, okay. The file name is the validate one. Okay.
May I?
Okay. Wait. I see. I try to run from my computer. Okay. Tough. So you want to use string.io to print the decision tree, is it true?
This is validate code, sir.
Validate. Because for validation,
This is the
we
one.
will for validation we have to calculate the accuracy.
This is for
Can you this I cannot hear quite clear. Or Tough, can you send
Sir?
me? Yeah, no, I can hear you. Okay. Oh, it's okay, Tough.
Okay.
Maybe you can try. Please send to my email your questions,
Okay,
and
sir.
yeah, so I can modify the program and send it back to you. Okay.
Okay. Thank you
Okay.
so much, sir.
You're welcome. Okay, so I think we finished the clustering today. You can try to do your homework. Uh, let's try in 1 week. I think in 1 week is enough. But in case you really get some problem, you just send me by email. Okay, we can discuss by email. Okay, and next week we will learn about association rules mining.